Because we are now live from downtown Mill Bay. Live from downtown Mill Bay. We are B Block. Woo. We did core notation. Now, did we write them down from last time? Yeah, we did. So, reminder, core notation. Put the square brackets of the previous noble gas, so it has to be on the row above. And then you put in the electrons afterwards. These would be the valence electrons. However, there's a little trick to that, so we're going to do valence electrons next. Let's do that one. And there's some specific examples, so let me pull those up, because I think that will help. So, for here, I would like you, with core notation, do the following electronic structure in pencil. Not pen, because you might have. Also, just as a general rule, unless I tell you, you should never be writing in pen. Science classes are never, they're always in pencil, because you have to like do things and erase things and check things, and which is in gallium, the electronic structure of vanadium. There is a time, however, you do your work in science with a pen, and that's if you're writing in a lab, hardbound lab notebook. There's specific rules for scientific notebooks. They are hardbound. They are not allowed to leave the room. They must be signed by your supervisor every single day. All data in them must never be whited out or erased, and you have to write in pen. If there are mistakes, you simply cross it out with a single line, and you write in the new information, and you have your supervisor write it. A grade 3 class that corresponded to all those rules charged a major Alberta oil company with environmental damage, and their lab books held up in court because the grade 3 teacher signed them off every day, and they were just doing local stream keepers, and they're measuring the pH of the stream every single day, and one day the pH just like plummeted to like 0 because upstream the mining, I think it was a mining company, not an oil company, released a sulfuric acid tailings pond into the stream. Just killed everything. And they were able to record it, and the judge was like, scientific data, I don't care who did it, and it's been being signed off every day. Go Holland. Pardon? They sign off because, what are you looking for? There's extra handouts up here if that's what you're looking for. Why do your supervisor have to sign off? Often it's because to make sure that they've checked your data and you haven't made any mistakes. A lot of science is about being objective, and so a second pair of eyes shows that you're trying to be objective. There's a hand up over here somewhere. If to the nearest noble gas, the noble gas. Because the noble gas represents the previous core, the non-valence electrons. So please write it out for vanadium and gallium. I'm going to come around, take a look at what you're doing. You've got guesses for all of them. Excellent. As what we were doing last day? Yeah. So do it for gallium and vanadium, and then take your best guess for +1 and +3 of gallium. What would be really helpful is the handout from last day. Yep. You got one. What might be helpful as you use your periodic table from last day is this handout. Yep. And actually, while you're doing this, I should probably do attendance quick. Yeah, with core notation. So you don't have to do the whole sequence. You can take the previous one as read. Come on. Let's go. Block B, attendance. Alexander, Anton. Where's Anton? Anton's not here. Cahalan's here. Donald's here. Evan's here. Henry is here. Hyundai's here. Jacob. Joffrey? Don't think I've seen him. He's also away. Jonathan Hannah. Silly boys in their soccer. Soccer. That sounds like I have an accent. Joshua. Kate. Oh, there you are. And Keith. There, I just saw you. Martin. And Ned. And Richard. And Sasha. And Will. So most of it's just those silly soccer people. Excellent. Okay, just point to your, I want to at least see your gallium and vanadium. Point to it as I walk by so I can just make it out easily. There's those ones. Let's see it. Can I see your gallium? 2 is 2, 4p6. Gallium? You are missing something in your gallium. Where's gallium? Right. So which noble gas do you use? Yeah, you did that. So starting over here, you would have, what S would that be? Nope. Count from the top. So you're going from the same area that gallium is in. No, gallium is there, so you'd be at 4s. And how many? No. Remember here, these are the S's. So 1, 2, 1, 2. So 4s, 2. Excellent. And then what's this? You just count your way along, but what is it though? Because it's not the P. What is it in there? D, yeah. And since we're on the first row, which D? Right. Perfect. Now count your way along. Nope, because it ends here. So it ends where this box ends. So you don't consider that, and you don't consider the first two. So that's the only D. So how many are there now? 10. Excellent. So it's 3D10. Now you only have this. Yeah. Excellent. And when you're where you start off, like you kind of 1s2, 2s2, 2, like 1s, 2s, 3s, 4s. P start at 2, 2s, 2p, 3p, 4p, and D start at 3, 3d, 4d, 5d. So it's 1, 2, 3 for remembering that. Okay? Okay. Senora, show me your gallium. Where's gallium? Right, so it can't be krypton, it's in the same row. Because you have to put all the things in for gallium. So you always use the one on the previous row. Yeah. And then you have it, because you've then said, I've read up to there, and then you just start on 4s. 1, 2, 3, 4. Yeah. 0.2 gallium, gallium. Excellent. Gallium. Nice. Yeah. Yeah, it's like you're going back. 0.2 at least your gallium. Oh, I was looking for gallium and you were pointing at that one. I got confused. That's fine though. Da-da-da-da. Yep. Da-da-da-da. Ooh, you made a little table. Pretty. No, it's nicely organized. Yeah, no, like I said that is nice. Excellent. Where's your gallium? Ah, pull this out. Oops. I want this gallium. Where's the previous noble gas? So first, where's gallium? Where's the previous noble gas? Oh, that's the noble gas in the same row. It's not up there yet. You want the previous noble gas. Now, in the row it's in, you start. Two S, 3S, 4S. 4S, and then how many? No. You count down increases the number in front. But across, you're counting the number of electrons in it. So as you go across, this is 4s1, 4s2. So altogether, 4s2. Right. And then we'll work on the next one. So for gallium, 4s2. And then what is this one here? That's 3D. And how many? Three D10, yep. And then what's over? For P1. Gallium. Oh, you need to put corn. You just did extra work. Yeah. It is beautiful. Can you do it in core notation afterwards? Because it will make it a little less confusing. Oh, yeah. So you can't use this one because it's in the same row. So you just go to the one previous. So it'd be argon. Oh, argon, 1s2, 2s2, 2p. So you just go argon, and then you start at 1, 2, 3, 4. So this is going to start at 4s2. So argon replaces everything up to 4s2. Yeah. Okay. Oh, it looks like I still have writing on the board. So, now that I've seen everybody who has done it, I'll just ask someone to tell it to me. Ned, what's gallium? He just left. Ned, what's gallium? Perfect. Now, I haven't checked everybody's vanadium, so I'm assuming everybody's done gallium, and we can work through vanadium if you haven't done it yet. Up next would be Keith. Perfect. Now, underneath there's a little note, valence electrons, those not in the core and not in the filled subshells. So what I'm going to ask for both of these is, what is the valence electrons? No, overall, for gallium, how many valence electrons does it have? Oh, you've said it Who said that? Yes? Who said that? Because it's the whole row. I heard the word 3. I just didn't know who said it. Excellent. So you said there's 3 electrons here. Why? Oh, okay. So you used the rule from last year. Perfect. How many valence electrons are there in here? No. Yes? Oh, no. I want the number of valence electrons in here. It's 5. Oh, well, let's go through both of the rules from last year that if you were in my class you learned, and if you weren't in my class you're going to teach you now. So the old Bohr model rules for valence electrons. Let me grab this. Were you just count in the row. Because it was 2, 8, 8, 18, everything was simple, and we said if I have boron, I would count 1, 2, 3. 3 valence electrons. How many valence electrons does oxygen have, please? Jacob. How many valence electrons does aluminum have? Richard. Louder. 3. 1, 2, 3. Oxygen was 1, 2, 3, 4, 5, 6. And this is still true because this is the 2s. 2s2, 2p4, 2 plus 4 is 6. So it also works for quantum. It's still true here. We have 3s2, 3p1. They're both in the 3rd energy level. So 1 plus 2 is still 3. So you're still doing the same thing for valence electrons. But when it comes to something like gallium, what was the rule for last year? If I said, what are the number of valence electrons of gallium? Hand if you remember the rule from last year. No, I'm going to pick on somebody I know I taught. But I'll see randomly. Who comes up? Donald. Donald comes up. Now you've kind of already answered. What was just the rule? Yeah, we don't care about the part in the middle. It was 1, 2, skip a few, 3. We skipped this. The rule was we skipped the transition metals. So I'll do nickel in a moment. So, but if I was to ask you, Ned, what is the valence electrons for arsenic, you would tell 5. You'd also be wondering, am I trying to poison? So we go 1, 2, skip a few, 3, 4, 5. The reason for that is what energy level are these? If I was to do the electronic structure and I did square bracket argon, and I'm going all the way to arsenic, what orbitals are these? These? 4s. What orbitals are these? 3d. They're 3, not 4. Once it's completely full, the orbital actually drops in energy and is no longer available as valence electrons. But to answer your question, what about, did you say nickel? Nickel or copper, any of these. So if it's not full, it's still there and available to be filled. So how many valence electrons, knowing that, Ned, does nickel have? Count. Yeah. Yeah. So what we have here is 4s2. It's okay, Ned. It's just fine. It's fine. Counting was a long time ago. You're not expected to remember. We have 4s2, 3d8 for nickel, right? That 3d8 is not full, so they still count as valence electrons. So 8 plus 2 is 10. All of it fills up. How many valence electrons would we then have for zirconium? please, Joshua. 4. And how many valence electrons would we have for tin? Please, Kate. Pardon? 4. Because once this is full, we skip it. How many would we have? Skill testing question. For zinc, please, Henry. It is 12. Because you're thinking about these 10, but you have to add those ones. So zinc, even though it's full, it is considered to have 12. Now that being said, because it is full, it will actually tend to use these more than those, but we would say they're still available, so we have 12 valence electrons. This is why a lot of the colored elements are in here. Rust is like that nice red color. Copper gives you blues and greens. It's because they have so many electrons to play around with. They end up doing stuff to light that other electron configurations can't. So sodium doesn't have access to d orbitals. It's just a white powder. It's not actually particularly interesting in terms of looking at. A lot of the colored metals come out of here because of the ability to use their d orbitals. Once they're full, though, boom, these are not so much. Arsenic, salt of arsenic is a plain white powder, odorless, tasteless, and used in Agatha Christie novels to kill people. Now, knowing that, I'm now going to ask, where's my clone? There it is. Gallium +1. What do you have to do when you have a +1 ion to change the electronic structure? Please, Ehunde. You add what charge are electrons? You take away another one. Which one do you want to take away? Yeah, you take away 4p1. So that's the electronic structure of gallium +1. At gallium +3, we have to take away 2 more. What one should I take away? Martin. So you would take that and make it 3d8? Yeah, that's incorrect. It is exactly, I've led you down that garden path. It's not incorrect because you weren't paying attention. But it is incorrect because what happens to these Ds once they're full? They drop in energy and they go down and join their buddies in the 3rd energy level. So what's left on top? The 4s. So actually these ones leave. Yeah. 4s, yeah, it's just left with 3d10s. Because the D10 with the Ds, once they were full, they're not part of the valence electrons anymore. Once they're full, yeah. 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 Because S and P are always in the same, because this is 4s2 at 3d10 4p1. So you still take off the p orbital first. And one of the reasons I'm making sure I'm using core is you don't take away from the core, and so that forces you to make sure you don't go into there, because that would be crazy talk. So valence electrons are those not in the core and not in the filled D or F subshells. This is also true for the F, but we don't talk a lot about the F orbitals, mostly because it's the same rules, it's just a little bit more complex, and we don't need to do that. So to add electronic structure and positive ions, the rule when you're pulling off electrons is P before S before D. The 4p orbital was pulled off first, and it was on the outer edge, and that made sense. But then we jumped over to the S. So P before S, but S before D. And I'll also write that down as an actual sentence, as opposed to just leaving that to that little mnemonic. So in an English sentence, when removing electrons for positive ions, remove p orbitals before S, and remove S before D. The p orbitals make sense, but this is the part. Oops. There we go. That'll get you. D orbital's full. Yeah. Hold it. When the d orbital is completely full, you skip it. But it also, I haven't done that example. I should just do that example. Never mind. So let's do then do for me, these should just a normal tin. Tin plus 4, tin plus 2, and then one example that addresses Ned's question. However, I want you to give you an example that you're not going to do in your Hebden. What section is this in? There we go. Perfect. So I will not give you that example, but I will give you zirconium plus 2, because your book does not. That was a really good question. Do those. Got them? Oh, nice diagram. Now, you might want to use the periodic table method, because you're going to get a periodic table in your test. You're not going to get that. Unless you can recreate that on your test, in which case, absolutely, yeah. Yeah, but you're just not going to have that on your test. But if until that point that's useful to use, absolutely. That's why I gave you a handout. So, oh, there's hands up. Yeah. 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 You got one of them? One of them before you go, then at least you won't be lost when you come back. Yeah. So 10 is, yeah, you'd use krypton. Yep. Yep. What S2? 1, 2, 3, 4, 5. Perfect. Yep. Oh, no. 3D. No, it starts 1, 2, 3. So 3, 4. What? 2. Yes. No. No. The part I'm saying no to is that you said P. These are d orbitals. For D10. Perfect. Yeah. 5p2. Yes. Lovely. Yeah. Perfect. Sorry, what? What about them? Oh, we'll go over them, but you're doing the right things. Oh, you're just doing them all in a row. Just efficiency. Alexander. 2. That looks good. Good, good. Something's wrong. Oh, that's not zinc. No. And you're forgiven for thinking so, given the quality of my writing. So I will fix this. However, this is not zinc at the very bottom. It's zirconium. Although, even this thought it was zinc, so fair enough. But please, it doesn't make sense as zinc because it's not going to illustrate the point I want to illustrate. So just so you know, it is zirconium. If you did zinc, that was what you did was correct for zinc. But just do zirconium underneath it. Oh, what did you have for zinc? Yeah. 5s2, 3d10. Yeah, but it was also zinc plus 2. So which ones would you take off if it was... Oh, you erased it. No, never mind. Never mind. If you erased it, it's fine. You just do it in the next question. It's okay. Zirconium, yeah. Yep, okay, so you've got things down. Now, just you might want to think about the rule we just learned. Now for this one, you had to take off 4 electrons. Sn plus 4? Yep. So which electrons do you take off? P before S before D. So what one will be left? Yeah. Right. We'll have to find out. But what was the rule we learned? Did the rule say unless? No, it didn't. Yeah. Yeah. I will make my way up. Good. So that one you just have to figure out which 4 you're going to get rid of. Sasha? Looking good. Mm-hmm. Okay. Okay. Oh, I'm not going to tell you. We're going to do it on the board. But what I want you to have is strengthen your conviction. You did something, and you took a chance. Oh, yeah, sure. Because you're about to run out of power? Always bring your charger. What kind of charger do you need? Is that an iPad? Okay, never mind. The aggressiveness of nothing you have will work. On the other hand, it is true. Okay, I'll ask someone for tin. Evan. Yeah. Excellent. Cajolan? For, no, for tin plus 4. Which electrons are you going to get rid of? Did you do tin? Okay. Then you can still do this one because you have to get, it's plus 4, so you have to get rid of 4 electrons. Which ones are you going to get rid of? In our rules, which ones do you get rid of first? P, so we can take away those 2. Perfect. Did it on the fly. Which should make the next one fairly easy. Oops. I'm going to do something with my phone. It keeps shutting off. Sasha? And then Ned, you have to answer your own question. What'd you pick? What is this? What noble gas does it start with? Okay. And here's where I get to say no. Because just plain old zirconium is 5s2, 4d2, right? And what's our rule? P, S before D. So we remove the S. And it doesn't say, the rule doesn't say S before D only when the D is filled, which is what you might have thought given my explanation, and I totally get that. This is a bit of a trick. Because it still, the S comes off first because it's the 5th energy level. You would think so, yeah. But it doesn't. Because it's the 5th energy level. Not the 4th, the 5th. 5th comes off first. Oh, I can answer that. Excellent. That is beyond the scope of this course. And if you ask that question in second year university, you know what they'd say? It's the beyond the scope. Because the actual answer, and here's the actual answer, is because there's only 2 forces involved here. There's the attraction of the protons to the electrons, so there's an electrostatic attraction to the orbitals, and there's the repulsions of the orbitals between each other. And that's not nice Bohr model spheres. These are complicated structured orbitals, as you have seen. And so those create complicated interactions. And so at the end of the day, the atoms just do something that's more efficient. So they fill up this way, 4s, 3d, unfill s before d, because those are further on the outside. And they just do that. Because the practical answer is when we take a spectrographic analysis of the atom of calcium plus 2, it's missing its s orbitals, not its d, and we can actually tell that out in tell that in an experiment. The actual reason is that it's complicated. No. Well, yeah, because the 5th ones are on the outside. No, it's just that's basically it. Well, it kind of is, because the the 5th one on the outside involves math I literally cannot do. Yeah. 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 Say university. When I did, we didn't do this part in high school. Like quantum chemistry wasn't in grade 11 chemistry and grade 12 chemistry when I took chemistry. Not that I remember much of it, um, because I didn't do that well in it. If you're having any hopes for the future, can I go on in chemistry? Have I told you what my mark was in grade 12 chemistry? Yeah. I hated chemistry. It was terrible. Like, who would ever take that? And then I got to university, and I was going into honors physics. I got an A in that. I liked physics. And then I noticed everybody in physics, they were all the same gender, and they smelled. Literally half of them didn't know how to take a bath. And I was like, these are not my people. Like, I like science, but these people like science in a way that interferes with their personal hygiene. So I transferred into computer coding, and I found out those people were worse. So then I transferred. The chemistry people seemed to be having fun, so I transferred into there. I had to work really hard because guess what I didn't do in high school? I didn't do my Hebden. They had a proto-Hebden. It was written by, it wasn't your Hebden. It was actually only this big. It was like a proto-Hebden. And it had like half the number of questions. So I actually learned on Hebden, but a completely, nascent Hebden that was growing, one might say. Yes. Always default to the rule. Oh, there is no exceptions to the rule except for the two exceptions I'm going to show you. Would you like to know the exceptions now? Never mind, he says. So, hold it, I need my mouse. So let's go down to, no, we already did that. So let's just use this blank page. I'll copy this title it. Exceptions to electronic structure. And I want to give me, in pencil, the electronic structure of copper. I've used a lot of red lately. Let's not bleed all over the page. Let's, nice, stark black. Copper and chromium. Alexander, what's the nearest noble gas for copper? Argon. And do you have the rest of the electronic structure? And then chromium. Let's go with Will. What is the previous noble gas for chromium? Argon. Excellent. Perfect. Four. Excellent. Now, this is one of those, this is our prediction. And by the way, what we've been doing so far is known as the electronic structure. We're following what's called the Offbow Rule, where we're filling it up from the bottom up. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Like, that's the Offbow Rule. It's German. It's not someone's name. I think it means foundation building. Build up. Yeah. So it literally means, like, it wasn't named after someone. It was actually practically named, but in German. So it's known as the Offbow Rule or the Offbow Principle. This is an exception to the Offbow Rule. And the exception is because if we actually measure these, so we do a spectrographic analysis and say, where are the electrons? It turns out the electrons are not here. They are actually 4s1, 3d10. And this I can answer. Yes and no. And I'll explain what I mean by yes and no after. Half full S or D subshells are stable. Half full. So D5 and S1 are stable. Completely full shells are stable. S2, D10 are stable. P's are also stable when they're full, and we don't worry too much about half-filled P's. They don't play much of a role in this. Unfilled D shells, D3, D9, D4, not stable. So unfilled D shells that are not half full are particularly unstable. So what would it want to do to this one? Oh, you can't get to 3d10, 3d5. Borrow that electron. So, sure. So take away that electron and make it 4s1, 3d5 stable. Now, is there a rule for exception? For example, chromium took an electron out of its S, put it in here, and then got a structure D5. Like manganese is D5. It is 4s2 D5 for manganese. Chromium has 4s1 D5. It's a little bit more stable. Would the same thing be true of tungsten? It does have the f orbitals, but it could still, they're completely full by this point. Yeah. So does tungsten do that? No. The tungsten obeys the Offbow principle. Chromium does not. And the secret is that there are some exceptions. The exceptions do not have a rule. And at the end of the day, this is because atoms are real things. These aren't rules like mathematical rules. Math rules are always followed because in mathematics you have called naive solution. Areas of math that are broken, in math you just pretend they work, and then math is fine. We don't do that in science. In science we say, well, this clearly breaks the rule. Our rules are not, they're descriptive, not prescriptive. They describe what we know. So the only two exceptions I'm expecting you to know is chromium and copper. Because it's not true for every member of the chromium family, and it's not true for every member of the copper family. And these are the two most famous exceptions that you would be expected to know in first-year university, so they're important to know. But there's other ones. There's a random smattering. I'll get you two questions in a moment. Now, just in case you talk to members of Mr. Snow's class, I don't know what he's teaching this year, but in the past, some chemistry teachers say the rule applies to all of them. And that's wrong. And some chemistry teachers don't teach the exceptions at all. And that's also not helpful because there are exceptions. So my compromise is that I teach you two of the exceptions. I vaguely hand wave and say that there are more, but you're not expected to know it. But some of them are exceptions and some of them are not. Our reasoning is true, but one thing to remember is that there's, again, only two forces here. There's the attraction of the protons to the electrons. There's the repulsion of the electrons to the other electrons. And those forces are incredibly complicated because of the shape of the orbitals. And so at the end of the day, what the atom does is just hit the lowest energy level. And sometimes that means getting a half-full D shell is more stable, and sometimes it is not. At this level, with 74 protons, the electrons are moving at near the speed of light. Whereas at this level, with only 24 protons, they're not. And so just different factors come into play. And the calculations required for me to even understand that, I can't do, but I can observe the spectrograph and say, well, that one does it and that one doesn't. But if you do the math, this one might. So we're not sure. There, and then Sasha, and then there. Yes, Will. So for what? Scandium? Where's what? Oh, yeah? Why? It can't fill up halfway, and it can't fill up all the way, so it would always be 4s2 3d1. Yeah. Yeah, they're always unstable, but this is why scandium has two ions. It has scandium plus 2, where it gets rid of the s, but scandium plus 3 is very popular. Scandium plus 3 happens all the time, because scandium solves that by becoming an ion and getting rid of all 3 of its electrons. Unstable doesn't mean doesn't occur. It just means it wants to react. Yeah. And unstable, they might do something about it by reacting. Chromium does something by borrowing electrons and then reacting, and that's why chromium plus 1, because it has 5 electrons here now, chromium plus 1 gets rid of that 1s electron and is happy. Chromium plus 1 is a very common ion for chromium because it doesn't have 2s electrons to get rid of. No. Oh, you're thinking of chromate and those such things. It's not -1 in real life. But it may be if you're doing, have you done oxidation reduction? If you calculate its oxidation number, which is a fake way of calculating its charge that it would have if it was engaging ionic bonding, which it's not, yeah. But it'll engage in some covalent bonding. Yeah, because that is particularly stable. And so it sometimes does covalent stuff like these ones do. It wants to hang on to its electrons. And that's why we get chromate and chromite and hyperchlorate chromate and stuff like that. Polyatomics we'll see later. Sasha, did I call on you? Okay. Was it Evan? Yeah. Oh, if they reached the speed of light, they would have infinite mass, suck everything around them into a black hole, which would slowly consume the Earth. Yeah, black holes wouldn't happen. There's a theory that... No, it has an immeasurable mass. We measure the mass of black holes in suns, and you can have micro black holes that have a mass of like 5 protons. As you run faster, you weigh more. Your mass increases. Its mass becomes infinite. Yeah. Yeah. No, the event horizon would be very small because it would shrink. Yeah. So you'd have a small, dense place. Now, that being said, can stuff cross that event horizon? Yeah, but really slowly because there's not much there. Only when black holes are very large do you start getting to see them. There's a hypothesis that there are black holes at both the center of our planet and the center of our sun that are providing some mass to hold these things in place. And they wouldn't consume the planet or the sun because they grow, when they're small, they grow extremely slowly. Conspiracy? Well, a conspiracy would imply that, like, the government did it. It's just a hypothesis. Some scientists have proposed it, and other scientists have said that's nonsense, and someone said, that's very interesting. Can we test that? Remember, as a scientist, you want to come up with things that you think aren't true and try to disprove them. Right? Did I do the 248 example? Oh, okay. I am thinking of sequence of numbers in my head, and that corresponds to a mathematical rule. I will give you a sequence of numbers, then you repeat a sequence of numbers back to me, and then you guess the rule. I will tell you if your sequence of numbers corresponds to my rule, and I will tell you if your version of the rule is correct. So my sequence of numbers is 2, 4, 8. Volunteer for give me a sequence of numbers back. That corresponds to what you think the rule is. Joshua, I think you're a fraction of a second first. That matches my rule. What do you think the rule is? That is not my rule. Yes. Have you seen this? Oh, you have to give me a sequence first. That sequence matches my rule. It is not an exponential rule. Give me a sequence. That matches my rule. What's my rule? That is not my rule. The sequence matches my rule. That is not my rule. The sequence matches my rule, and that is my rule. And so that example is used to show the importance in science. People start out by guessing things they think correspond to rules. And that's why your question was so good before, because you asked about something that didn't correspond to the rule. So when I say 2, 4, 8, when you repeat 16, 32, 64 back at me, you haven't changed anything, so you don't get any new information. You know 2, 4, 8 corresponds to the rule, so 16, 32, 64 probably will too, but you haven't learned anything. But if you said 0, -1, and 3, then you'd learn something. That doesn't correspond to my rule. If you said 1, 2, 3, that does correspond to my rule, and it also tells you it's not doubling. If you said 0.5, 0.75, you would also learn something about corresponding to rules. So you always want to propose things in science you think aren't true and test them. That's because science is not a painting, it's a sculpture. You take things away, you don't add. We are now done quantum chemistry. Well, we add by taking away, because nothing in science is 100% proved, right? So, number one, everything could be true. So we assume, well, okay, all of this isn't true until you prove it. Let's start with a model and then try and disprove the model. So you're always trying to disprove parts of your model. Science is a practical method, which is why people who try and find meaning in it, you can't find meaning in the scientific method because it's by definition set up not to find meaning. It's set up to find facts. And not even facts. It's set up to disprove facts. Yeah. Yeah. Probably. Well, because science doesn't say it's sad or happy or anything. It just this is what is. But meaning of whether or not it is sad or whether it's good or whether it's bad, science can't tell you that. Hold it. Did I not give 4 out? Yeah. I thought, can you continue passing one back? I passed the 3-hole punch around as well. Someone was said, I think, and I don't know if it was this class or different class, they were like, Mr. Neufeld, will we get review sheets? And I said, no. Because you're in Chemistry 11, a senior science course. You have your Hebden and your notes, you have tons of practice. And then I felt bad. So I did make a brief review sheet out. This review sheet does not cover everything. If you go through all the terms and you know them all, then you're doing pretty good. Are there terms missing? Absolutely. So if you don't know a term, you should probably go back to that section, see what you know. If you do all the questions and you can do them, do you know everything? You might. That's a good sign. If you can't do a question, does that mean if you study that one question, that's what you need to do? Probably not. You probably need to go back to that whole section and learn what it is that you missed in order to do that. But this should give you a sort of a little guidepost, bumping up from what now. I've already posted the day of the test. When's the test? November 9th, which is Tuesday. Question, Sasha? Yeah. It's like the giant crab. I'm so shiny. Why? What things are shiny? Metals. It's a property of metals. So like one of the questions in there is like list all the properties of francium. Well, you could say it's highly reactive, but you also know it's a metal. So you can say it's shiny, conducts electricity, conducts heat. Like it's all the properties of metals. Pardon? After December break? I mean, I think term 1 reports are sooner than that, and term 2 sport does a different day. My brain just says when we have a break, the first term is done, because that's what it feels like. I don't know. Yeah, people are nodding. And this is the longest term. Yes? No. Why do you want a stock pot? You'll have to check with your house. I tend to use an Instant Pot because then instead of taking 3 days to make stock, I can take 3 hours. Yep. The questions I am getting, it is always better to leave it as it is, bandage it, and let it do what it has to do. Okay, I don't know what the rowers do because they're a completely different species. But the reason popping your blister is bad, Cahalan? The reason popping your blister is bad is now you open it to infection, and you can rub all that skin away and tear off new skin. Yeah, rowers have to row with blisters, so I don't know how that works. What? It never goes away. Do eventually you get calluses thick enough you don't? Oh, okay. Now, before we continue on with blisters, which I don't know quite how we got on. Oh, Cahalan asked the question. You have the rest of this class then to start your Hebden, start going through your notes for your study notes. You have time to catch up on, you should have all the assignments in. I've given back your quiz. You can go over that. So it's study time now for your test next week. Or if you've done all that, you've got a review piece, which I was so nice to give out. So nice. Go on. If I said, get me the electronic structure of oxygen, would you be able to do that? Okay, go to that section of your Hebden and start doing those problems and bring them all up to me. Okay, try the first one, get it wrong, bring it to me, let's go over it. Because it's much easier at this point to go over questions you can't get. So go to that section of there's a Hebden list, and instead of doing start with the ones assigned and then just keep going. So pull out your Hebden. Do you have your Hebden? Go grab your stuff. Here and then there. Yeah, it ran out of battery. Was this the drawings of the S, P, and D orbitals? So you need to be able to, did you get the handout of what they look like? Yeah. Okay. So practically, go to the handout, if you can find it. Practically, you were only expected to draw on a test the S and P. I don't know if you do have it if you weren't here. Oh, there you go. So you're only expected to draw the S and P. And how they differ is that for the S, it's just a sphere, and then you put in the axes, but it's a sphere, so it all looks the same. The PX has the lobes going out along the x-axis. Oh, yes. So the reason these have weird names, all of these, you'll notice, are in between the axes. They're not on the axes. So DXY, the lobes are in the plane of XY, but they're not on the axes. They're in between them. DXZ, the same. They're in between the axes, but now they're in the XZ plane. Okay. Same with DYZ. Now we're in the plane of YZ, and they're in between. Yeah, so so if you rotated the quadrants, that one, and that one would look the same. You would just change your labeling. That one is because we already have an XY. Right here, right? So the difference between that one and that one is this one was in between the axes, and that one was rotated and is dead on the axes. Different perspectives. Now you should be able to draw these, and you should be able to label these. So if I showed you that one with the axes correctly labeled, you should say, oh, that's a DYZ. I won't ask you to draw it. It's along the X. Z. Well, they're trying to show this by the elongation to show that they are spread out this way. So they're up and down on the Z and back and forth on the X. The XY flips them that way. If that helps. Yeah. And you should be able to look at any of these and go, not which one, and just say, that's an F orbital because it looks too complicated. Yeah. Here and then there. You should keep this in case you ever... No, you don't have to keep the printouts, no. Yeah. But keep the notebook for any ones you have to do in there if you have to hand it in the future. Yep. Nope, that's the next unit. So we haven't done... I'm about to move that. We've now done everything up to, but not including Lewis structures. Yeah, I was just going to go down one. Is there another hand up? No? Okay. And we are... Excellent. Oh, and I can stop it recording.